Welcome everyone to your online pre-calculus course. Tonight's section is 4.3, right angle trigonometry. And our objectives for this section are going to be to use right triangles to evaluate trig functions. We're going to find the function values for some other important angles like 30 degrees, pi over 6 radians, 45 degrees, which we've already done a little bit in the previous section, and 60 degrees, which is pi over 3 radians. And then we're going to use equal cofunctions of complements and this identity that lets us go back and forth between sines and cosines. And finally, we're going to use right triangle trigonometry to solve applications, which means word problems. All right, so let's get into this a little bit. Okay, so first, we've defined trig functions in the previous section based on a circle. So what we said was that we have this circle, the radius is 1, which makes it a unit circle, and somewhere this angle, right, as this angle opens up, is going to intersect this circle somewhere. And this coordinate right here represents 2 points, x and a y coordinate, right? So this coordinate represents a point on this function, or a point on this circle, and then we have these special new trig functions, sines, cosines, and tangents, which give me one of these 2 coordinates. What we're going to do today is we're going to now take this definition and make it in terms of a right triangle. Okay, so here's a better picture here. So the first figure, right, figure A, shows a central angle that measures pi over 3 radians. And the arc, the blue one, is also pi over 3 by definition, right? If the radius is 1, this arc length right there is the angle times the radius. Okay, so pi over 3 times 1 is just pi over 3. In figure B, we can turn this situation into a right triangle, right? I just drop a line straight down, and now I have a right triangle with the hypotenuse being the radius of this circle, and the x and the y coordinate being the 2 sides of the right triangle. Okay, so we can now think of pi over 3, right? This angle right here, okay, right there. We can also think of it as 60 degrees because it's a little weird to think of the insides of a triangle as a radian measure. So when we're talking about triangles, we are going to go back to using degrees. So we can think of 60 degrees as the measure of the acute angle in that right triangle. And because sine is the second coordinate and cosine is the first, sine is the y coordinate, and cosine is the x coordinate, okay? If you look at this picture, right, the sine would be the y coordinate, y. But we also want to divide out the length of the hypotenuse. And this is something we really didn't get into because when we were talking about the unit circle definition, this was always 1, so it didn't matter. But in this case now, this hypotenuse can be anything we want, and we set up a ratio. So the sine of 60 degrees is equal to y, which is the same thing as y over 1. The cosine is x, which is the same thing as x over 1. And when we do this with certain kinds of problems, it's helpful to interpret these trig functions and right triangles when we are limited by the way triangles work, okay? Triangles, a right triangle especially, has a 90-degree angle, and then it has 2 other acute angles. So we're always limited to acute angles. So we can label this triangle ABC. The sides are angles, notation here, angles are always capital letters when we talk about in trigonometry. Angles, we're always going to use capital letters. Sides are always going to be lowercase angles. Angle A and side A will always be across from each other. Okay, so this side is the hypotenuse, right? Because it's across from the right angle. If we were talking about this angle, if theta is right there at A, this is the side opposite, right? It's opposite of theta. It's not touching that angle. This, B, is the side adjacent, okay? And we can set up our 6 trig ratios in terms of these ideas of a triangle. So we can say that the sine is the length of the side opposite over the length of the hypotenuse. The cosine is the length of the side adjacent over hypotenuse. Tangent would be opposite over adjacent. And then my reciprocal identities just get flipped over. So hypotenuse over opposite, hypotenuse over adjacent, adjacent over hypotenuse. So hopefully you guys see where this is going here. And each of our trig functions of the acute angle theta is positive, okay? And then of course these are, like I just said, these are all reciprocals, okay? And these have to be positive because the lengths are length, they're going to be a positive length, okay? So hopefully in geometry you learned a little trick to remember this using this mnemonic device. All right, SOHCAHTOA. Okay, usually we like to write it with a little dash in here. Okay, SOHCAHTOA. All right, and it stands for sine is the opposite over the hypotenuse. Cosine is the adjacent over hypotenuse, and tangent is the opposite over the adjacent. Okay? You could just remember that sort of name. There's a joking story about an Indian chief who kicked a rock really hard and ran down to the river to soak his aching toe, and the clan or the tribe then called him Chief SOHCAHTOA because he went to soak his toe in the water. Silly joke, but it could help you remember this little mnemonic device, and it helps get these ratios: opposite hypotenuse, opposite adjacent, for the 3 trig functions. And if we look at 4 different triangles, in each of these triangles, right, theta is always the same. Okay, in this case, it's 56.3. Why? Doesn't matter what it is. But all of these triangles, if you remember in geometry, are similar because the angles are all the same, but the sides are different. Okay, that means they're also proportional. Okay, and it also means that the tangent in all of these, remember tangent, right? The tangent of theta would be the opposite side over the adjacent side. So it would be 3 over 2 here, 6 over 4 here, 1.5 over 1 and 4.5 over 3 are all going to be the same. They're all going to reduce to 3 over 2. So that gives us something very, very important, that in general, trigonometric function values of theta depend only on the size of the angle and do not depend on the size of the triangle, okay? Because these things are ratios. So that means that the tangent of this triangle and the tangent of this, the tangent of this angle in this triangle and the tangent of this angle in this triangle are always going to be the same. All right, so let's find some trig functions using SOHCAHTOA. Okay, so we're going to find the value for each of the 6 trig functions. Well, before I do that, I need to know how big all the sides are. And hopefully you remember the theorem that helps us find the third side of a right triangle, which is the Pythagorean theorem. A squared plus b squared is equal to c squared. So we have 5 squared plus 12 squared is equal to c squared. 25 plus 144, which is 169, 169, and square root both sides. My answer can't be negative because we're talking about the side of a triangle, and it works out perfectly to 13. And if a right triangle has all sides that are integers, those three numbers are actually called something called a Pythagorean triple. Okay, so 5, 12, 13, pretty common one. And if you see a two of those or a multiple of two of those, you should be able to get the third side fairly quickly without having to do the Pythagorean theorem. Right? You're going to start recognizing these very quickly. This and the next one are very, very common. So the sine, the cosine, and the tangent of theta we can calculate using these two signs. Here's theta. It makes a difference. If theta was up here, then 12 would be opposite. But if you look, the side opposite of theta is 5. So the sine is the opposite over the hypotenuse. The cosine is the adjacent over the hypotenuse. And the tangent is the opposite over the adjacent. And then for my other three are just reciprocals of the first ones. So cosecant is 13 over 5. Secant is 13 over 12. And cotangent is 12 over 5. Okay. Let's do one more of those. So again, Pythagorean theorem. To find c, we have 3 squared plus 4 squared is equal to c squared. 9 plus 16. And this gives me another Pythagorean triple. This is the most common one. This is the one you should definitely try to recognize to save yourself the time that it took to find the third side of a right triangle. This is a 3, 4, 5 right triangle. 3, 4, 5, 5, 12, 13 are the two most common right triangles. So now that we have all three sides, we find the sine, the cosine, and the tangent using SOHCAHTOA. So the sine is the sine of this theta, right? That's where theta is. It doesn't always have to be there, okay? It could be one of the other two angles. So the sine is the opposite over the hypotenuse. The cosine is the adjacent over the hypotenuse. And the tangent is the opposite over the adjacent. My reciprocal identities, the cosecant, the secant, and the cotangent are just reciprocals. And I like to keep them in this order, right? Sine goes with cosecant, so it's easy to just flip that over. Cosine and secant are my reciprocals, and cotangent and tangent. Okay, and so those are the 6 trig values of theta. Now, it doesn't always have to be perfect. Remember, that is the hypotenuse, the side across from the right angle. Okay, so that means that a squared plus b squared is equal to c squared. So a is 1, b I don't know, and c is 3. Subtract 1 from both sides. B squared is equal to 8. Square root both sides. So b is equal to 2 square root 2. Okay. It's fine. It's a little uglier, but we're still going to do the same thing. So write this down if you have to. So SOHCAHTOA. Don't spell it wrong. SOHCAHTOA. Okay. All right. So the sine of theta, the cosine, and the tangent. Opposite over hypotenuse for sine. Opposite is 1, hypotenuse is 3. So we have 1/3 for sine. Cosine would be 2 radical 2 over 3. And the tangent would normally be 1 over 2 radical 2. But you should know this by now, you can't leave it like that, okay? You must rationalize the denominator. So I'm going to have to do this, and I get the square root of 2 over 4. Okay. Cosecant, secant, and cotangent. This would just be 3 over 1. Here, right, 3 over 2 square root 2. Can't leave it like that. Have to rationalize it again. So we get 3 square root 2 over 4. And then cotangent, I could flip this one over, but why not just go back to the beginning? That way I don't have to rationalize anything, okay? And those are my 6 trig values. So it's okay to get a radical, right? And it's going to be pretty normal to find triangles in this case with radicals in them. All right, let's do a couple of our special angles that we had talked a little bit about in the last section. So in 4.2, we use the circle to find values for the trig functions at pi over 4. Okay, how could we find the values for the trig functions at pi over 4 or 45 degrees using a right triangle? Well, hopefully you remember from geometry is that if you construct a right triangle with a 45-degree angle, like this one, 45-degree angle, the other angle has to be 45 as well. And that means the triangle is isosceles. And if we assume that each length of the triangle has a length equal to 1, you could assume it's anything because the size of the, remember what we just said, the size of the triangle does not affect the sine, cosine, and tangent, only the measure of the angles. So I can make the sides any length I want. It would be the easiest to make them 1, so that way we find the hypotenuse, 1 squared plus 1 squared is 2, boom, and we have our 45, 45, 90 triangle, okay? So if I'm looking at this 45 degrees here in the lower left, if I want to find the sine of 45 degrees, we see it's the opposite over the hypotenuse, which you can't leave like that, so we get the square root of 2 over 2. Hopefully, you recognize that from the last section. The cosine of 45 degrees is, again, that was the opposite. Now we have the adjacent. And so the adjacent would be 1 over radical 2 as well, so it's radical 2 over 2. And the tangent of 45 degrees is the opposite over the adjacent, which is 1. And then the other 3, we're just going to find the reciprocals here. So to find the cosecant, secant, and cotangent, it would just be flip this one over, right? So it would be radical 2, and still 1 for cotangent of 45, okay? So on the unit circle definition, right, we had to make this 1, and then we had to figure out the other sides, and we did some other stuff. With the right triangle definition, it doesn't matter what this length is right here. I can make it anything I want. And in this case, having the other sides be equal to 1 is a little bit easier, okay? So that is a 45, 45, 90 triangle. There's one other special triangle that we like to talk about in geometry, and that's a 30, 60, 90. 30, 60, 90 triangle. So 30 degrees, which is pi over 6 radians, and 60 degrees, which is pi over 3 radians. If I wanted to, again, I could make an equilateral triangle. Cutting it in half will let me prove this, that, again, I can make the sides I can make the sides any length that I want. So if I make this 2, if I cut this angle in half, which I want to do to drop an altitude here. Now, this is 2, this is 1. Pythagorean theorem gives me this side right here. And now we have our triangle ready for our ratios. Okay? So that means that the sine of 60 degrees, the cosine of 60 degrees, the sine of 30 degrees, and the cosine of 30 degrees are all on this triangle right here. So be careful at which angle you are looking at. So if I want the sine of 60, that's this angle. Sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. Okay? But if I want the sine and cosine of 30 degrees, now I'm looking at the angle at the top. Now 1 becomes the opposite, 2 is still the hypotenuse, and the adjacent side is the square root of 3. Okay? Let's throw in tangents. And also notice that the sine of 60 and the cosine of 30 are equal, and these two are equal too. We'll talk a little bit about that more later. But the tangent of 60 degrees would be the opposite over the adjacent. The tangent of 30 degrees would be the opposite over the adjacent, which I have to rationalize, which gives me radical 3 over 3. Okay. So, when we are calculating these special angles, right, these numbers are very common, right? These are the things that we are going to recognize all the time. And in fact, because we'll use them so often, the 30 degrees, the 45, and the 60 degrees, you should learn all these values for each angle. The sine, the cosine, the tangent of each of these special triangle angles. The 30-degree angle, the 45-degree angles, and the 60 degrees angles. Okay? Once you have the three of those, it's pretty easy to get the cosecant, secant, and cotangent, right? You just take the reciprocal. But it is very, very helpful to remember that these, what these values are. And you can notice that the sine, the value is actually going up because as we radical 2 divided by 2 is 0.7, and radical 3 divided by 3 is, oops, radical 3 divided by 2 is 0.86, right? This is 0.5. So because the sine represents the y coordinate on a unit circle, as I'm going around, look, I'm going higher. Cosine's going down because as I go around this way, I'm getting closer to the x-axis. And the tangent is weird because it's a ratio. But now, something really special can happen. We now know every single thing about this circle. We can fill in all the different degree angles, radian angle, sines, cosines, and tangents for all of these different functions. Okay, so let's try it. Let's do degrees first. 30. Remember I said go around by 30s? 90, 120, 150, 180, right? We're just adding 30 degrees to get all these different angles. 210, 240, 270, 300, 330. I just added 30 degrees. Now I'm going to go around it again, adding 45, 90, 135, 180, 225, and 270, and 315. You can recognize some other patterns here, right? That 45 is 15. The middle one is 15 away from the 2 that it's in between. And yeah, this is also 360. Okay, as I go around once. Let's do radians now. We start with 0 radians, and we start with pi over 6 radians. And now what I like to do is just go all the way around, keep adding pi over 6, just like I kept adding 30. So we get pi over 3, pi over 2, 2 pi over 3, right? 1 pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6, and then 5 pi over 6, and 6 pi over 6, reducing each one as I go. This is 7 pi over 6, 4 pi over 3, 3 pi over 2, 5 pi over 3, and 11 pi over 6. 1, 2, 3, 4, 5, 6 pi over 6, 7, 8, 9, 10, 11, and 12 pi over 6, 2 pi. Spin around once with pi over 6, then I fill in the pi over 4s. That's 1, 2, 3, 4, 5, 6, and 7. Okay? Now, when I fill in my coordinates, I usually like to do the quadrantal angles first because I know that this is 1, 0. This is -1, 0. This is 0, +1 because I went up, and 0, -1 because I went down. So I did degrees, I did radians. Now I'm going to do sines, cosines, and tangents. So remember, sines and cosines just means the y coordinate and the x coordinate, and tangent is the y over x coordinate. Okay? And these numbers come from the triangles that we were just making. So the 30-degree angle, right, the sine was, if we go back, the sine of 30 degrees was 1/2, and the cosine was radical 3 over 2. So that's my first coordinate, 1/2 radical 3 over 2. Sorry, wrong way. Okay, it goes x comma y, so it's cosine comma the cosine of my angle comma the sine of my angle. Okay, so don't get those backwards like I just did. Okay, so cosine would be radical 3 over 2, 1/2. This one, the 45-degree angle, was radical 2 over 2, radical 2 over 2, both the same because it's a 45, 45, 90 triangle. And then the 60 degrees was now the reverse of this one. Okay. Now, all these coordinates are positive because we're in the first quadrant and everything's positive. The rest of this circle is really easy to make once you do the first quadrant because you just reflect everything over. This and this coordinate are the same thing. Okay? We'll talk about why in a later section, but they have the same values. The only difference is the x coordinate there is negative because I'm going to the left of the origin. So this coordinate right here, instead of being 1/2, would be a -1/2 and a radical 3 over 2. This one would be negative radical 2 over 2, negative, and radical 2 over 2. This one would be negative radical 3 over 2 and 1/2. Down here, they are both negative. This coordinate and this coordinate are the same thing. So it's negative radical 3 over 2 and negative 1/2. Both of them are negative here and here. Reflect it down, it's the same thing, except they're both negative. Over here, reflect it down, right? So this would be a positive 1/2, because x coordinate is positive, a negative radical 3 over 2, because we're going down, right? And then down, and everything else follows along. So even though this looks a little crazy and the writing's not perfect, but we're now able to fill in the sine and the cosine. Now we just need the tangent. Okay, so the tangent for 45 is easy, it's 1. Okay, now we just have to remember the tangent for those two angles. So 30 degrees and 60 degrees. Okay, so 30 degrees is radical 3 over 3, and this one's radical 3. again, once you get the first quadrant, the rest is easy, but we also need the quadrantal angles. So remember what tangent is. Y divided by x. So the tangent at 0 is 0, but the tangent up here, y divided by x, is undefined. So this is also 0, and this is also undefined. Okay? Now, the tangents are the same all the way across, except now we have a positive divided by a negative, so it's negative radical 3, negative 1, negative radical 3 over 3. Negative divided by a negative is now a positive, so that's positive radical 3 over 3, positive 1, positive radical 3, and back to negative in the third quadrant. Okay? And so that is the full unit circle with degrees, radians, cosines, sines, and tangents. Okay? So this is something that you really need to start to remember. I would suggest finding a blank one in line and practice going through it, because knowing these basic angles, the sines and cosines of these basic angles, is very helpful. I'll also post a link to another video, something called the left-hand rule, that can help you remember some of these things in the first quadrant. And once you know the first quadrant, again, everything, right? All of these are the same, right? They all have the same coordinates. They all have the same over 3 in their radian measure, right? These are all the same. And these are the same as well. So the unit circle has a lot of pattern in it, right? You just have to be able to pick them out and sort of remember kind of how they work. And the key is the first quadrant from there to there. If you can get all that, you should be pretty well off, okay? But let's move on. Okay, so we talked a little bit about how these points and these points are pretty similar, okay? So let's get into that a little bit. So two positive angles are complement. Remember that from geometry? If their sum is 90, or pi over 2 radians. So 7 and 20 are complements because they add up to 90. So in the last section, we used the unit circle to establish fundamental trig identities. Another relationship, remember that, is that the sine was equal to 1 over the secant, and the tangent was equal to the sine over the cosine, right? Those are the fundamental relationships, fundamental identities. So another relationship that we can use is based on angles that are complements, okay? And look at this. If we're looking at theta, the sine of theta would be opposite over hypotenuse. So it would be A over C, okay? But what about the cosine of that angle, whatever it happens to be? 90 minus theta. Well, cosine is adjacent over hypotenuse. And we can see just by going to the other side of the triangle, and these two things always have to be complements in a right triangle, we can see that these two things are going to be equal to each other. And that's pretty much what this says right here, right? The sine is going to be A over C. The cosine of this angle up top is going to be A over C as well. So therefore, the sine of theta is equal to the cosine of the complement of theta. And if you ever wondered why one is called sine and the other is called cosine, because cosine is a shortened form of the phrase complements sine, cosine. And they happen to be called cofunctions of each other. And any pair of trig functions, f and g, for which f of theta is equal to g of the complement of theta, is going to be a cofunctions. So we can show that tangent and cotangent are cofunctions, and secant and cosecant are cofunctions as well. So we have some identities that say that. So sine and cosine go together. Either way, sine is equal to the cosine of 90 minus theta, or the cosine is equal to the sine of 90 minus theta, either way. Tangent and cotangent go together. Secant and cosecant go together. All these are with 90 degrees. The same applies to pi over 2 radians. It doesn't matter. They both mean the same thing. Okay? And what we can do with this is we can just do some nice simple problems here where find a cofunction. So that means that this is equal to something with 90 minus theta. Okay, so the sine of 72 is the same thing as the cosine of 18 degrees. That's all there is to it, right? Just 90 minus theta, these two things will be the same. Works with radians too. So cosecant is equal to the secant of 90 pi over 2 minus pi over 3. Just don't get lost with a common denominator, and you get pi over 6. Okay? So let's use some of this stuff for some word problems. So many applications of right triangle trigonometry involve an angle made with a horizontal line, usually imaginary. Okay? So the figure's on the next page, but if we have an angle formed by a horizontal line and a line of sight above the horizontal line, that's called an angle of elevation. If we look down, right, that's called an angle of depression. Some tools that are used to measure these kind of angles, transits and sextants are both instruments that use to measure angles from a site. I have a picture of those. So here's the picture they were talking about. So if you're standing on a balcony, right, the horizontal line, right, the horizon is the straight line straight in front of you. If you look up at the plane, that's an angle of elevation. You look down at a car, that is an angle of depression. Okay? And the tools that you would use to measure them are one of these, right? Transits, sextants if you wanted a tool, or you could just use trigonometry. Okay? So now the hardest part about these word problems, I think, is you really should, if you're not given one, you really should make a picture. Okay? So, sighting the top of the building, a surveyor measured the angle of elevation to be 22 degrees. The transit is 5 feet above the ground and 300 feet from the building. So, imagine what's going on is you're standing here, you are measuring, right, a building. Here's the building, right? You're looking up at the top. Here's your flat line. The angle is 22 degrees. The height, from here to here is 300. That's important. And the transit 5 feet above the ground. Okay? Terrible drawing. Here's a better one. So basically we're going to find this. We're going to find the height of the building using our right triangle, and then we're just going to have to add this 5 feet back in to find the true height of the building. Okay? And we can decide which trigonometric function to use based on SOHCAHTOA. Okay, so let's see. What do I know? What do I need? I know this. My angle. So I have an angle. I have the opposite side. I want the adjacent side. I have the adjacent side. I want the opposite side. So we're going to use tangent. So the tangent of 22 degrees is going to be equal to some number divided by 300. So we just multiply both sides by 300. So the 300 tangent of 22 degrees is equal to A. Now, you just need a calculator. But we did a lot of, okay, so we did a lot of stuff in the last section with radians. So you really need to know how to change your calculator back and forth from degrees to radians. And I have to do that right now because my calculator is in radians. Okay, so flip it back to degrees, and I'm going to take 300 times the tangent of 22. And you should get that A is equal to 121 point, what does it say to round to? Doesn't say, whatever. We'll round to 1 decimal, 20.2 feet. Okay, that's A. And now we just add 5 to that. And so the height of the building is 126.2 feet. Now, if your calculator was in radians, you would have gotten a really weird answer, like 300 times the tangent of 22 would have given me 2.6. That doesn't make a lot of sense. Okay? This building is probably not 2.6 feet high. So especially if you get a really, really big answer or a really small answer, definitely check to make sure you are in the right mode. All right, so let's set up another one real quick. This one provides the figure for you. Okay, that's great. That makes the question way easier, right? And we have the same situation. We have an angle. I have my adjacent side. I want my opposite side. So I would use the tangent of 24. It's not always going to be tangent, right? You can know this side, or you can any way that this works is just pick the right trig ratio. Is A over 750. Let me switch back to degrees, and we have 750 times the tangent of 24 gives me 333.9. In this case, we're in yards. Make sense? Sure, right? This is a big number, but this is a smaller angle, so a smaller side should be across from a smaller angle. Okay. Now, in both of these cases, I knew the angle. Okay? If you know two sides of a right triangle, an approximate trig function can be used to find the angle, to solve for the angle. Okay? You need to find the key to do this on your calculator. It is usually right above the key for sine, okay? And it's called the inverse sine, okay? Usually looks like this. Most calculators have the inverse sine, cosine, and tangent button all right there. No real calculators do secant, cosecant, or cotangent, but for right triangles, we are not really going to use those too much. We're not really going to need to figure out the reciprocal identities. Figure out where it is on your calculator, figure out how to get there. Most of them are going to involve pressing like a shift or a blue button or some sort of second function button to get up to the little writing above the word sign. And if you do it right, you should get, right, something like this. So if you wanted to do the inverse sine of 0.866, you should get about 60 degrees. Okay, let's try it. Yeah, if you get around this, right, you get 59 point, or they just say, yeah, 59.997. Okay, so what that means is that if we have this picture and we want to solve for an angle of elevation, right, I know two sides. What two sides do I know? Okay, I know, here's my angle, I know the opposite, sorry, I know the opposite, I know the adjacent, that is the tangent. So the tangent of theta is equal to 21 over 25. Now what I'm doing here is I'm taking the inverse tangent of both sides. Now you don't have to go through this each time, but I wanted to sort of show you how it works. This says take the tangent and then do the inverse tangent, and so these two, what happens is they just undo each other and you go back to where you started. Remember that f inverse of f of x was always just equal to x. Okay, so if you're starting in this angle, if I'm taking the tangent of that angle and then taking the inverse tangent of that angle, this outputs an angle. So it's saying, what angle has a tangent of theta? Well, theta. Okay. So now we just need our calculator to calculate the 21 over 25 inverse tangent, and I get 40.03. And be sure that my angle is in degrees. Okay. So there's a couple problems like this on the homework, so definitely you should practice as much as possible in order to get a little bit better with this. Okay, and that was section 4-3, right angle trigonometry.